Prestige Engineering. I'm the project manager, Steven. Our team consists of German Alonso, Anola Panzon, Oscar Sosa, Anzel Ayala, Jose Villa, Jonathan Fernandez, and Camilo Torres. And we're going to talk to you today about our final plan for how to come and attack the Bridge 9 and the development on the SR 826, 836 interchange. So just a brief overview of our entire presentation. We're pretty much just going to go straight to the point, how we're going to go ahead and plan and design it, how we're going to go ahead and develop it, and in general, our team of engineers are going to go ahead and explain that. And just so everybody knows what we're talking about specifically, that's Bridge 9 right here. It connects SR 826 to SR 836 going westbound. Alright, and without further ado, I'll give it to our geotechnical engineer.
Alright, good evening. My name is Hansel and I'm the geotech engineer. Right here we have an overview layout of Bridge 9, and this right here indicates where the boreholes are going to be located within the bridge. We estimate a total of 12 borings, 2 at the end vents and 10 following where the pier paths are going to be in the bridge. Right here we have an overview of the soil classifications for the bridge around the span of the bridge, and the top layer mostly consisted of fill, limestone, silt, sands, organic material, and high water content. Middle layers consist of limestone with calcareous fine sand, and lower layer 2. The top layer will receive a blow count of around 3 to 8 blows because it's really weak soil. And once you go further down, you'll get to a better blow count in order to construct in this bridge. And we're going to be using standard penetration test for this. Right here we have an overview of the foundation for the piers. This pier is going to take a lot of power, so we're using driven power method, which is a defoundation method because of the nature of the superstructure, which is going to need the ability to resist a lot of loads. And now I'll pass it on to my colleague Camilo Torres to further explain the structural.
Thank you, Hansel. Good evening, everyone. My name is Camilo Torres. I'm one of the 2 head structural engineers assigned to the project. So, Bridge 9 is to be a segmental bridge. It will be composed of a total of 244 sections, or segments, however you want to call it. Spans 6 and 7 will be the longest ones, they'll contain a total of 25 sections each. The highest point of the structure will be located on top of pier segment 7 with a total elevation of 91 feet. So how we're planning to build this? Balanced cantilever method using a gantry system will be the mean for installation of the segments that will make up the superstructure. The process starts by installing a pier segment, and after that sections are progressively attached to each side of it to keep it balanced. The purpose behind it is to avoid inducing large bending moments to the connections and the piers. Every time a new section is attached to a cantilever, it is kept in place by temporary post-tension steel tendons. For the case of Bridge 9, the maximum loads that the structure will ever experience occur during the construction process. It is important to keep in mind that the gantry exerts a total of 950 kilopounds applied to the bridge as 2 point loads that are located in the supports, the front support and the rear support. This table that you see here shows the design loads for the most intense load condition that the bridge will have. It occurs during the erection process just before the mid-span section that joins the span that runs from pier 7 to pier 6, it's installed. Now I'm going to hand it over to my colleague, Jose.
Thank you, Camilo. Hello, my name is Jose Villa, and I'm the other structural engineer. The pier design is just going to be like you see on the picture. It's basically composed by 3 main sections. On top of the power cap, that is going to be a solid section, followed by a hollow section, and then the pier cap. All the pier caps are going to be the same in dimension for all the piers. The construction of those is going to be in place and mass concrete technique is going to be used given the volume of concrete that will take to make it. For the superstructures, since we choose the segmental bridge post tension, this is one of the sections that goes right on top of the pier. As we can see, we have the deviator that guides the tendon right on the top, so that's going to be basically to follow the design moment. And then on the right we can see the groove tongue system that is going to be implemented in order to increase shear capacity. The post tension process is going to be, like Camilo said, it's going to be when we are attaching the segments, it's going to be kept in place by temporary post tension tendons, and then after that the permanent tendons are going to be installed. The amount of tendons and the place where they run is going to be governed by the design. For a general case, or for this case as well, we're expecting to have the bigger positive moment at the mid-span, therefore the tendons are going to run at the bottom. At the piers, that is the biggest negative moment, therefore the tendons run at the top. Then we're going to stress the tendons, and it's going to be protected following FDOT standards. The post tension has great benefit. It provides great bending moment resistance. The erection process is easier compared to the other methods that we thought about. And then since the tendons are exposed, it facilitates the grouting process, and it avoids mistakes and other complications. Now I'm going to pass it on to
Thank you. Hello everyone, my name is German Alonso and I'm the water engineer. We were able to put together a very efficient and cost-effective and aesthetically pleasing design because you barely see the pipes. So we basically designed for a high intensity of 3.94 inches per hour and one of our design criteria was to keep the spread at a maximum of 11 feet, so just keeping the water outside of the traveling lanes. So this is how the system will work. We will put inlets on the left of the sections looking up station, and in every span, every middle span, but span 8 and 9, because those are the highest ones. So we basically going to collect the water through the inlets and bring it inside of the segments. And so this is what a picture of what the inlet looks like. So now after we collect the water and bring it inside of the segments, we will bring it down through 6-inch PVC pipes and 9 out and landing on top of a splash pad. In like I said, in every pier but pier 9 and 10. I'm sorry, 8 and 9. Now getting the water out of the bridge deck is one thing, but controlling it and then to minimize hazards, we had to design 2 detention ponds. 1 detention pond by pier 11 and 1 detention pond by pier 7. I'm gonna hand it over to the environmental engineer.
Thank you, Jeremy. Good afternoon. My name is Jonathan and I'll be talking about the environmental part. As Jeremy said, we had to design a detention pond 2.7 and 2.5, and we're going to have within the ponds a French drain that will discharge the water to the ground, that will minimize the discharge into a canal, which we will also be discharging through a U-type concrete end wall. Moreover, this is a picture of the U-type concrete end wall, and during construction we will minimize pollutions by doing phase construction activities. We will minimize any, we're going to sterilize all the project as soon as possible. We're going to protect slopes, protect strong drain inlets from any sediments that could possibly go into on-site or off-site. For solid waste, we're going to designate an area for the solid waste, recycle materials whenever possible, and reuse and schedule the waste collection to avoid overfilling of the containers and making sure they have leads. For air quality, it's actually very important, since if not handled properly on-site, it could affect off-site as well. And research has linked the fine air particles in the atmosphere with respiratory problems. So for this, we're gonna limit the vehicle speed on site, and we're gonna water with a water-based surf again. All exposed surfaces on a daily basis. Maintain engines, avoid overloading. Again, these are all mitigation practices that we'll be doing. Washing vehicles wheels before they leave the site. Noise and vibration is inevitable. So for this, we'll be letting the public know through the media what time it would affect them the most. But either way, we're gonna reroute the trucks away from residential areas, and if there's no any other alternative, we're gonna find a path with a few homes. Combine noisy operations rather than one at a time, and mufflers on engines, and use noisy equipment as far as possible from the residential areas. Also, one part of the environmental that I want to talk about was the existing of the Florida manatees that are actually the Tamiami Canal. It's actually their habitat, so we'll be putting some type of fence on the water to prevent them from going into it. And now I'll pass it over to Oscar also.
Good afternoon, my name is Oscar. I'll be the transportation engineer for our project. Some of the things that are very important that we need to handle with our project is stopping sight distance. Typically, the driver's sight is about 3.5 feet from the road. That's why we will be implementing a 32-inch area on the inside of our curve, as well as we will have a 40-mile-per-hour design speed on our curve. Again, our curves are going to be F-type, as we said earlier in our proposal. Alright, for vertical alignment, we have to worry about the airplane. You know, AASHTO has its regulations of at least 14.5 feet. But since we're a little bit southern of the airport, we won't have to deal with that. Now, there are two corridors that do run under our project, which is A26 and A36. So we have a minimum clearance of 16 feet with an additional 6 inches for future milling and resurfacing. For our super elevation, we follow the PPM respectively with a 40-mile-per-hour speed limit and a 5-degree curvature. We do have a 6% super elevation for our curve. This is our typical section. As you can tell, it's 2 travel lanes of 12 feet, 10 feet shoulder on the inside, a 6-foot shoulder on the outside, with a possible third lane that could be added if level service does not improve in the future. Again, we did speak about MOT before, but we did implement the original plans where we're not, if any lanes have to get closed, there will be closed at night, typically around 10 or 11 till 5 a.m. And pretty much the motive behind our MOT is to make sure that we're able to guide our drivers through the construction site without any problems. Now I'm going to go ahead and pass it over to our aesthetics.
Thank you, Oscar. Hi, my name is Anola Fanson. I'm going to be talking about the aesthetics of the project, and later on I'll be presenting the cost estimates to you. Okay, so this bridge, since it's a high visible bridge, is classified as level 2 aesthetics by the FDOT, and also, as we all know, the FDOT partnered with the Miami-Dade Expressway Authority to complete this project. So the aesthetics of this project are going to be framed by this MDX enhancement manual, including the color scheme, the piers, the retaining walls, and the lighting. The color scheme for this project is going to be based on previous project, just to keep an aesthetically pleasing transition, and then also the similar similar elements will have the same colors to be consistent. For the piers, the pier caps will be flared, and the piers will have a constant cross-section area throughout the whole column. And they're also gonna have, like you see here in the picture, a band with the palm front finish, as the MDX enhancement manual describes. Now, the retaining walls will be MSC walls, and will also have the palm front finish, and will be squares as the FDOT requires. Now I'm gonna pass it over to Steve.
So I'll be talking to you guys about the lighting and what we chose for the lighting. Pretty much for the most part, we chose the basic standard aluminum poles for the lighting. The aluminum poles are going to range between 25 and 50 feet depending on where they're placed on the bridge. Other than that, they have 6-foot arms, and they're just your general standard aluminum poles for the most part. For placement, they're going to be placed on the outer part of the bridge, but connected to it on the inner curve. As you can see right here, this is basically going to show you more or less how they're going to be placed along the bridge throughout the design. Now, for the bulbs, we wanted to do something a little different. Instead of doing the standard HPS bulbs, which are high pressure sodium, we wanted to go ahead and implement LED bulbs, which are far more efficient, far more cost effective in the long run, and they're far less maintenance. Also, they have a really good benefit of actually being aesthetically pleasing compared to your standard bulbs. They're going to light the roadway far more, and you're actually going to create a safer environment for the drivers as they're able to see the lines and markings more visibly. Through this, we need to get the permits from FDOT MDX to make sure that we're able to proceed with our plans for this. And then continue on to the scheduling. The scheduling, for the most part, is generalized at the point, since we haven't started the construction yet, in that sense. But with everything in due time, we project that we're going to finish this project, should we be awarded it, by February 4th, 2017. And in total, we're going to have about 185 days of designing, and the end time for the construction is going to be 469 days of on-field construction. Now, that's just basically a broken down, simplified version of the schedule. We didn't include in there things for let's say the mobilization. We didn't put a temporary electrical power. We didn't put temporary water. We kind of generalized it for the most part. The most important things to note on this schedule is the fact that we're going to be on the field, as I said, for 469 days. That's how much time we're expecting to be there, and causing a disturbance, having to put barricades, having to reroute traffic, and by the end of the schedule, should be completed by February 4th, 2017. And the schedule is subject to decrease in time as we continue to further crash schedule the development. We get to the point where we get the gantry. As you see, the gantry is right about here. And when we're going to get it and when we're going to put it together, it's all dependent on the time of the gantry mostly for that part. And now I'll go into cost estimates, and Anola will explain that.
Well, as you can see here, we have the cost estimates broken down for you. Here is a most specific how we divide it. It's the substructure, the superstructure, the miscellaneous, and the life cost, which round up to $10.6 million for a total cost. And
Okay. All right, so that's our plan. Any questions?
Just to clarify, I guess something for me regarding, I saw the spread was 11 feet. Is that the total spread?
Max, we want to keep the spread at a maximum of 11 feet, which is the shoulder width, the left shoulder width looking up station.
I thought drainage manual talked about limiting the spread to half the lane of the travel lane. Anyways, just, yeah, I thought it went into the travel lane and not just the shoulder, because people typically just ride on the actual travel lane, and that's where you really want to limit the hydroplaning and all that stuff. I guess the limits as far as vertical construction of the bridges is, I saw it's apparently controlled by ASHTO. Spoke on that. Was it ASHTO?
Yes, sir. Just to become actual compliant with the actual upgrade and downgrade of our curve.
I think that's more on the design aspect, but someone you have to coordinate. One of the entities, I believe, is the FAA. You got to coordinate with them as far as what kind of vertical construction, when the gantry, but in this case, the gantry is further south. I don't know what that zone is. I don't have more questions on that.
Yeah, explain your negative moment at your piers.
Explain negative moments.
You want to do it?
It doesn't matter. It's just like negative moments.
Scott, that's what I thought I heard you say.
Yeah.
Negative,
Well,
maximum negative moment at the pier.
well, it's basically for, I don't know. This is the actual bridge. It's an indeterminate structure. We will require a modeling system to determine that. But for a simple bend, always the bigger maximum moment occurs at mid-span, the negative moment will occur at the pier.
But how do you have a moment at the pier where you have a connection?
Because it's fixed supported.
The three middle of pier caps are fixed connections. With
Oh,
the-
okay. So your
Yeah.
moments are on your pier caps, not on your superstructure.
It's in the pier.
It's in the
Oh,
pier.
okay, you're talking about the pier then. So your maximum moment is in the span,
Yes.
maximum positive moment, but you say your maximum negative moment is in the pier cap.
The maximum positive moment is in the span.
Right.
The maximum negative moment it's in
Okay, so it wasn't clear that you were talking about the piers and not the span. That was my confusion.
Okay.
Why would you have a moment on the span at the pier? That was my question. Either I misunderstood you, or that's how you said it. But okay, but you answered my question. What is your design criteria for your tendons themselves?
tendons itself.
Yeah, what kind of, like your tendons are what? Tension, compression, where are they in?
Tension all
Okay,
the time.
so what is your maximum, what is your tension load that you use to design the cross section on your tension, on your tendons?
I go back to this table that you see here. It displays the critical loads, the design loads in the critical case, critical load condition per se, which occurs here. This moment, it's a negative moment, and it is happening in this pier segment.
Okay, right. That's not what I'm asking. You're using your tension, your tendons are going to go through the bottom of your span at the midpoint of your span, correct?
Yes.
So what is your load there, and how do you design the cross section on your tendons? What load are you using to design those cross sections on your tendons? The required cross sections are you?
For a mix of
What are you using to design the tensile strength of your tendons?
the moment capacity of the segment.
Which is,
24, 23.
what about your dead, that includes your dead loads and your live loads?
Yeah, it's all factored here. These are the reactions.
Okay,
These are the reactions.
Right.
This takes into account the combination, the load combination, and the safety factors.
and these loads are in service or in construction?
It's
Construction. This is during construction.
Okay, all right. Thank you. Just checking you did. Don't sweat it, dude, you did okay. Any other questions? Okay, good, thank you.